This is the introduction to our functions unit. This is to watch right before you go through a series of IXL reviews and also a couple new things. Just to go through our review first, maybe you don't remember, but there's something called a relation. A relation is basically what it sounds like. It's a connection between two numbers, okay? One of the numbers is an input, the other number is an output. Usually we call the input X and we call the output Y. Often we make it an XY table like this. We've used these in our warm-ups and in some of our work so far. When we've plotted things, we usually have a pair of numbers. There's the left number and the right number. The left numbers are X values, the right numbers are Y values. Okay, usually we put them in a table like this. There's also a different representation here, which is called a mapping. A mapping has two spaces. It's got the left space and the right space. The left space is called the domain, and the right space is called the range. Easy to remember which one goes on the left because in the alphabet D comes before R, so D comes first, R comes second. Hey, what do you know? X comes first, Y comes second, also in the alphabet. So the domain goes with X, the range goes with Y. The reason why we call this representation a mapping is because the way we pair the numbers is we draw an arrow from the left number to the right number. And actually you can kind of see that the mapping here is actually the exact same mapping that sits in this table, right? There's a 211 pair here. Look, I have 211 here, and there is an arrow showing that 2 maps to 11, okay? Do you see how there's two pairs here, 211, 212, they both start with 2? Well, when you do a mapping, you only show the 2 in once. And then how do you show it mapping to both 11 and 12? Well, you draw two arrows. You draw one arrow going to 11 and the other arrow going to 12. That's how you show that there are two pairs that start with 2. In the table, you just put two different rows, right? Easy, right? Next representation. Everybody's really familiar with graphs, right? So in a graph, we just have a point which represents the mapping. The mapping is between the domain, or the X values, to the range, or the Y values. The domain, or the X values, are the input. It goes across the bottom. And then the range, or the Y, or the output, goes across the top. A lot of people tend to forget which one is X and which one is Y. I always have a mental image in my mind about the relationship between the horizontal and vertical here. I always think of it like this. If you have a wall in your house and you are going to hang a picture up on the wall and you need a ladder to hang up on the picture on the wall, well, the first thing you're going to do is you are going to walk to the position where you're going to hang up the picture, right? Once you get to that position where you're going to hang up the picture, then you take your ladder and you climb up to hang up your picture, okay? So the reason why I think of that is because you always move horizontally because it's easier to move horizontally, right? And then when you want to go to a high point on the wall, what you're going to do is set up your ladder once you've already moved horizontally, right? So I just use that analogy to remember that you always go horizontally before you go vertically, and then you always have X before Y also because it's in alphabetical order, right? So X must be the horizontal and Y must be the vertical, okay? Finally, there's the ordered pair representation. And this representation is very similar to the table representation. The only difference between the ordered pair representation and the table representation is the table is kind of vertically arranged, right? But I'm arranging these ordered pairs here in the table, and you can see that It's pretty much the same thing. The only difference is that the table is kind of a square thing, and the ordered pairs are parentheses and brackets around them. So, but otherwise, it's pretty much the same thing, right? Moving on. We're going to talk more specifically about domain and range. Remember, domain is all the possible valid x's, and the range is all the possible valid y's. So here it says, what is the range of this relation? So we're going to look at the dots of the points that are mapped here, and we're going to look at the y coordinate of these points. So for example, this one maps to -4. These two map to -2. This one maps to -1. Remember, I'm only looking at the y coordinates of these points. So I would say that the range, which is all the possible valid y values, includes -1, -2, and -4. And I've written those right here inside the brackets with commas. That's how we note the range in this case. Okay. What is the domain of this relation? So here they're giving us the relation in terms of ordered pairs. And the domain, remember, are the x values. So the x values are these here. So we have 13, 12, 5, and 5. Actually, we don't need to say 5 twice. We could just say 5 once, because if you say that 5 is in the domain, you don't need to say it every time that you have a relation. Okay? Moving on, let's talk about the difference between relation and function. Here's a story to help you understand. There were two guys. One guy's name was Relly. The other guy's name was Dr. Funk. They were both basketball players. Relly believed that wearing a certain pair of basketball shoes did not really affect his game, right? So like sometimes he would wear a pair of basketball shoes and he would play well, and sometimes he wouldn't play so well. Whereas Dr. Funk, he believed that if he wore certain pairs of basketball shoes, that he would always play well. And if he wore maybe some other pair of shoes, that he wouldn't play so well. Okay? So Relly is like a relation, and Dr. Funk is like a function. Okay? A function is like a pair of shoes, or a relation is like a pair of shoes. And if you wear those pair of shoes, a function believes that every time you wear a certain pair of shoes, your game is going to be at a certain level. It's always going to be at that level. Okay? It's never going to be at different levels. Whereas Relly believes that if he wears a certain pair of shoes, sometimes it's going to be at a certain level and sometimes it's going to be at another level. Okay? So like a function always takes the basketball player and maps him to a certain level. Okay? So it's not like it's going to map him to a 90 level player one day and a 70 level player the other day. If it maps him to a 90 one day, it's always going to map him to a 90. And a different pair of shoes might always map him to a 70, okay? But that player is always going to be mapped to a certain level with that pair of shoes, no matter what day it is, okay? So, on the other hand, Relly, when he wears a pair of shoes, sometimes he's going to play well and sometimes he's going to play bad. So sometimes a relation maps a basketball player to a 90 game, and sometimes it'll map him to a 70 game, and depends on the day. Okay? So let's look here at these results of wearing a certain pair of basketball shoes, and then we're going to see if this is a function or a relation. Okay? So let's say that each one of these inputs here is a certain basketball player. Do you see how this basketball player, when he wears these basketball shoes, he plays at this level? That's fine. He always plays at that level. That looks like it could be a function, right? What about this player? He's playing at two different levels, depending on the day. So that does not look like Dr. Funk. It looks like Relly, right? So it looks like a relationship. What about this one? This one is only one level. So that looks like it could be a function. So if you look at this group of points here, there is one set of points right here which is not a function. It maps to two different levels for the same pair of shoes for this basketball player. Okay? So this is not a function. It's a relation. So it's not a function. Okay? Let's look at a different representation. In this representation, we have our domain, which are the basketball players, and we have the mapping, which are the arrows, and we have the range, which is how good they play. And in this case, we can see that this function always maps certain players to certain levels. Okay? And there's no player being mapped to two different levels. What would that look like? It would look like this. If a player gets mapped to two different levels, it would have two arrows coming out of the same player. Okay? And that doesn't happen here, so this is indeed a function. Okay? What about the opposite? What if I had another player here, player number 5, and what if player number 5 also mapped to 16? Is that okay? Yeah, that's fine, right? Sometimes two players are going to get the same result out of the same pair of basketball shoes. That's fine. As long as 5 always maps to 16 and doesn't go to some other level, that's fine. So is this relation a function? Yes, it is. Now we're going to look at it at ordered pairs, okay? Ooh, look at this. We have player number 6 who maps sometimes to 10, sometimes to 20, sometimes to 4. Is that a function? No, that's a relation, right? Okay. Moving on. All right, now we're looking at a few other examples. This one's a table. In this table, 19 maps to 8, that's fine. 8 maps to 20, that's fine. But then look at this. -8 maps to two different values. So is that a function? Nope, it's a relation. Okay. What about here? We have a graph. Each player seems to map to one level, right? I'm drawing these lines to show that, like, this is one player, maps to one level. This is one player, maps to one level. This is one player, maps to one level. So that looks good. And what I just did is called the vertical line test. I draw vertical lines, and if the vertical lines only cuts through the function in one place, then it is indeed a function. Okay. What about this graph? If I do the vertical line test on this, I cut it in two places. So no, not a function. What about this? This looks like it might be a function, but if you have a solid dot here, that's just like the solid dots we encountered on the number lines we did. If you draw a vertical line through those two solid dots, are you crossing the function two different places? Yes, you are. So it's not a function. What about this one? This one has a lot of open dots and closed dots. Is there any place that we can do a vertical line test here and cross the function in two different places? If we cross here, we're actually going through two empty dots, open dots, so that we're not crossing the function at all. Here too, okay? What about here? If we cross here, we're crossing a solid dot and an open dot. The open dot, the function doesn't exist there. So the solid dot, we're crossing the function once. And then when we cross the open dot, we are not crossing the function. So it's fine. So yeah, this is a function. Okay. So that's enough about the difference between functions and relations. I hope you like my analogy. Here, we're looking at evaluation of functions. Okay. So for example, given a value of x, what's the value of y? Given a value of y, what's the value of x? Okay. So in this case, for example, it says, plot a point on the function with an x value of 8. Okay, x value of 8, remember x is here and y is here. Remember my analogy about hanging up the painting and having to walk across the floor before you put up the ladder, right? So here, x, I would go out to the 8, and now I'm going to go up here, and then I'm going to hang up the painting right there. it's at 8, comma 9, right? And then it says, what is the y value of this point? Well, the x value is 8. They gave that to us. And the y value happens to be 9. Okay, so we just get it by marking the point at x equals 8 on the line. Here's another one, except now they give us a y value. So they give us a y value. The y value they give us is 3. So now what we need to do is we need to figure out where on the y-axis we're looking. And we're looking right here at 3, right? So we're going to put a dot right there. I already put a dot there. And then I'm going to find the x value at this point. So I'm just going to draw a line down. And then I see that the x value at this point is 0. Okay? Here's a tricky one. It's a curve. Plot 2 points on this function with a y value of 4. So y value of 4 is right there, right? This is the y-axis, and there's the 4. So I'm going to draw a line cutting my function in 2 different places. So the places that I'm cutting happen to be the points I'm interested in. And after I plot the points, it says, what are the x values of these points? Well, I know the y value of the points. The y value of the points is 4. Now, if we write the coordinate pairs for these, this one is at -7, 4, and this one is at 0, 4. So what are the x values here? The x values would be -7 and 0, right? The y value is 4. So it would be -7, -7, and 0 are the x values of these 2 points. Okay. Let's talk about the reason for functions. We have been using y up till now to refer to all of our functions. What's wrong with just using y? Well, we've already done a few graphs on Desmos and other places where we've had like 2 graphs on the same axes. Remember the Pizza Hut and Domino's investigation? We had a Pizza Hut line and we had a Domino's line, right? It would be handy if when you have 2 lines or 2 functions on the same axes that you could call each one of those lines by a certain name. Okay, so like for example, let's say that we had the Domino's line, and then we also had the other line, which was a Pizza Hut line. Okay, wouldn't it be convenient if we could call the Pizza Hut line P and the Domino's line D instead of calling them both Y? Okay, so that's one of the reasons why we have function names, because sometimes you're dealing with more than one function. So we can give each of the functions we're dealing with a different letter, and then that helps us differentiate between the functions. Okay? Functions are also like rules or mappings that tell you how a pair of basketball shoes makes a player better or not, right? So like each pair of basketball shoes behaves differently according to Dr. Funk. So like one pair of basketball shoes would not have the same function name as another pair of basketball shoes because it behaves differently, right? So that's another reason why you would need 2 different names to refer to the same or to 2 different pairs of basketball shoes. Okay. Last of all, whenever you define a function, it always has a variable inside the parentheses. And this is the only variable in this expression. The function itself, the name of the function, is not really a variable. It's a rule, right? We know what the function rule is most of the time. It doesn't vary, so it's not a variable. The variable here is the input. It's like, who's the basketball player, basically, wearing that pair of basketball shoes? It's X. Most of the time, we define the input variable or the basketball player that's in the shoes as X. Okay? And then we define the rule according to X. So we can say g of X is equal to X plus 5, for example. Last thing, I'm going to talk about one of the most confusing things about function notation. Okay? I think function notation, which we just wrote here, g of x equals x plus 5, is quite confusing sometimes, and I'll show you the instance where it is confusing. Okay? If I put here g and I put x squared, or some kind of expression in the parentheses here, you know what I'm supposed to do? I'm supposed to replace any instance of x with x squared. Do you see what I just did there? That's very confusing. I had a value x here, and all of a sudden I replaced it with x squared because this x became x squared. Okay? Let me give you a hint about maybe a way that you could look at this differently than the traditional way. For example, you have g of x, right? And that g of x is x plus 5. I think that it might be better, and I'll show you why, if instead of thinking of g of x equals x plus y, if you said g parentheses, maintain the parentheses, and then put an underline sign to signify that it's blank, and then say, oh, g parentheses blank is equal to parentheses blank plus 5. Now, if I write it like this, there's two good things that happen. One is I know that the blank needs to be replaced with something. Okay, and I don't have the x there to confuse me if I'm going to replace it with another expression with x in it. The other good thing that the original expression doesn't have is I have parentheses here. The parentheses I have are inside my rule also, whereas like the original expression, you can see there is no parentheses here. It's good to have the parentheses there, and I'll show you a couple cases where if you don't put parentheses around what you're substituting in, you're going to get into trouble. Okay, so instead of writing g of x equals x plus 5, how about if you write g underline with parentheses around it equals underline with parentheses around it plus 5. Okay, all I did was replace the parentheses x with this other blank. Okay, now I'm going to show you why that reduces some confusion. Okay, so for example here, I have my rule f of x equals blah blah blah. Then here it says, hey look, take negative x and substitute it in for the x. Okay, now if I did that without parentheses, I would end up putting 8 minus 11x minus negative 6 squared. Okay, and if I did that, I might think, oh, I'm sorry, I forgot this x here. There's an x here too. 11, and then I'll put times minus 6 there, right? Now I'm going to write it with my suggested notation. With the suggested notation, I'm saying do f blank equals 8 minus 11 parentheses blank minus parentheses blank squared. Now I'm going to put in f of negative 6, and I'm going to put 8 minus 11, I'm going to put parentheses negative 6 minus parentheses negative 6 squared. Okay, now if I do this problem and I do this problem, I'm actually going to get two different results. Watch this. 8 and negative 6 times 11 is negative 66, and then minus minus is plus, and 6 squared is 36. Okay, and that'll give me negative 30 plus 8, which I think is negative 22. Okay, now I'm going to do the bottom one. The bottom one is 8 plus 66. And then here, I'm going to take negative 6 and multiply it times itself. We'll get positive 36, and that will give me negative 36. Now, if I add this up, I'm going to get 38. Did you see that? I got 38 here. I got negative 22 here. What's the reason for that? Because I didn't have parentheses here. The PEMDAS would tell me that I need to square the negative 6. I don't square the 6 and then do the negative afterwards. So you can see in these cases, the fact that we don't put normally parentheses around the input can confuse us, and we'll end up getting the wrong answer because of PEMDAS. Okay? The other thing that it helps us with is when we replace things with a variable. Okay? Like, for example, let's look at this one. The way this normally would be written is hx equals x squared minus 6x. Do you see all I did was replace it with the x because they're being nice to you in IXL by not using x's, but a lot of times we're going to see x's. So I have this expression, and then I'm going to substitute in, instead of negative 6j, normally they'll just say negative 6x. Okay? And then it's quite confusing to look at this and say, okay, wait a second. I'm replacing x's with negative 6x's. Okay? It's like I'm replacing one thing with another thing that looks exactly the same. In order to avoid that, again, I suggest writing it out like this. Okay? And then putting blanks in there. And now it's a little bit easier to see that if I write h negative 6x here, that all I need to do is put negative 6x squared minus 6, negative 6x, and all the parentheses are already there ready for PEMDAS. Okay? So this is going to give you a different result than if you don't put parentheses. So the parentheses are really important. Okay? So that's it. You're ready to do the IXL now.